In this section, we'll study three popular machine learning classifiers: logistic regression, support vector machine, and k-nearest neighbors. Let's begin with the standard logistic sigmoid function defined in this equation. The logistic function is often used for activation. It has good properties. It is the solution of this simple nonlinear differential equation. We can verify it easily, sigma prime. Then by using quotient rule, we reach at this one. And with algebra, we can simplify to become sigma times 1 minus sigma. So it is satisfying this differential equation. And when x equals 0, then you can easily see the value is half. So the logistic sigmoid function is the solution of this differential equation. Sigma prime is an even function, and it is rotationally symmetric. If you add sigma x and sigma minus x, then it's always 1 for every x. If you integrate the function, then you can reach a logarithm 1 plus e to the x, which is known as the soft plus, and it is a smooth approximation of the rectifier. Rectifier is defined in this way, taking maximum between x and 0. See this figure. This is a sigmoid function, standard sigmoid function, and this blue curve is the rectifier, taking maximum between x and 0. And soft plus is this smooth approximation of the rectifier. These three functions are quite often used for activation functions. Now we'll begin logistic regression. Logistic regression is a probabilistic model. The method maximizes the likelihood of the parameter W. In realization is quite similar to Adeline. Here the difference is the activation function. In Adeline, the identity is the activation function, so there's no activation. However, in logistic regression, we are using the sigmoid function for activation. And that's the only difference for the logistic regression. Okay. Because we are using the sigmoid function, the value, active value must be between 0 and 1. So the prediction can be interpreted as the probability of a particular sample belonging to class 1. Here, active value, the value must be between 0 and 1. Now, for x, and the probability of x belong to 1, class 1, upon the weights. Of course, z must be the net input. So we may interpret the activity value as the probability. And also there are some theory and to support this claim. In the class of machine learning, you learn the detail if you are in the class. let's try to derive the logistic cost function. And it starts with the likelihood, and it's defined in this way: phi, active value, and that is power. Now the label is used to power, and we assume this power is 0 and 1, and organized in this way. For each point, this term is multiplied. So once we can get W and B correctly, then for example, a point is belong to class 1, then this value will be ideally 1 and power 1, ideally 1, so that it'll be 0, and this is 0, so that anyway this will be 1. So once it is well classified or well trained, then this likelihood will be near 1. If not, then this likelihood will be lower than 1. Now, once we try to maximize this likelihood, then it's not easy because it's involving power and multiplication. So rather than this form, we try to maximize log likelihood. And by using the properties of logarithm, this power can go out, and multiplication would be changed to be addition in logarithm space. So we have that. Now, rather than maximum of this logarithm, and we try to minimize the negative log likelihood, that is exactly the objective function of logistic regression. Here we are using, for activation, the logistic sigmoid function. Okay, now we have to minimize this objective function. How? By using the gradient descent method, we can do that. And here, so we need to calculate the gradient, and negative gradient will be scaled by eta and update the parameters, the weights and bias. Okay, computation of the gradient of J for logistic regression from the objective function, and we make Wj directional derivative. Then by using chain rule, we can reach at this one, and then for that one, we can use the property. Already we know that the sigmoid function derivative is the same as sigmoid function times 1 minus the sigmoid function. And now by using chain rule, the coefficients of Wj must be here. For each component we reach at that one. So now, and along with that, we can simplify here. In vector form, we reach at that one. Similarly, for the derivative of J with respect to B, we reach at that one. Now, the coefficients of B is 1, so that we don't have that here. Now, we summarize the gradient descent learning for logistic regression in this algorithm. And W and B are updated along with the correction vector and correction term with learning rate eta. And that is the scaled minus gradient. And already we have here negation, so that we have here positive, and eta times this one. And gradient B is eta times that term here. Now this one has exactly same form as for the algorithm Adeline. And only the difference is here we are using activation function and sigmoid function, but in Adeline is identity. So there is no special change for the net input. But here we apply sigmoid function to get the value between 0 and 1, and that is the only difference. So that once you get the code for Adeline, then you can modify it quite easily to get a code for logistic regression. Okay, that's the end of part 1. We'll continue in the second part. Thank you.